So one of the last things we're going to look at is reciprocal functions. And that is when you have 1 over f of x. We've already done a number of special transformations. One of them, for example, is you've learned how to take the square root of any function. Do you remember doing that, where you kept 0 and 1 the same, and sometimes the graph was above and sometimes the graph was below? We had transformations which gave us all of our basic transformations, and then we have some special transformations. And one of them is 1 over f of x. If you have any graph on the bottom, what happens when you do 1 over that graph? Now, the 1 over f of x graph is not the same as f inverse of x. It is not the inverse function. So we don't write it ever like that. And you have these notes for special transformations. Now, the big idea, and if I wanted this lesson to be a 30-second lesson, then this is all I would tell you. If you have 1 over f of x graph, that means that any point on f of x, all that's going to happen to it is the y values change to 1 over y. That's the only thing that's going to happen. And if I wanted this to be a 30-second lesson, I'd say, good, we're done. Now go play with that, see what happens, and draw your graphs. Because that's enough information. That's all this lesson is. It's a special transformation. All that happens is your y values become 1 over y. If you think back to these graphs, all that happened was the y value got square rooted. Right? You just took your y value, kept x the same, and square rooted it. So it's similar to that. That only one thing happens. But despite that being the only thing that happens, there's some interesting things that we look at. And so I've highlighted them in this sheet. So let's look at some steps. If you were asked to graph a reciprocal graph 1 over f of x, the first thing you're going to do is graph your bottom function first. That will give you a whole bunch of y values and give you an idea of what your original graph looked like. Then, on a separate graph, we are going to draw vertical asymptotes wherever we have x-intercepts. Why? Because if we have an x-intercept, for example here, let's say on your original graph you have the point 3, 0, and if the only rule is that your y value becomes 1 over y, well then that 3, 0 is going to change to 3, 1 over 0. And that's bad. That's a non-permissible value. That's dividing by 0. And so what do we do whenever we divide by 0? Well, we've seen in graphs that that's either a hole in the graph or a vertical asymptote. And for reciprocal graphs, it'll always become a vertical asymptote. So I'm going to run through these steps, and then we're going to see it in a bunch of different examples. And I find when I'm learning something that seeing the steps, then seeing an example of how it works, then looking at the steps again really helps me understand what's going on. So we'll quickly run through the steps. After drawing your vertical asymptotes, you're going to look if your graph has a horizontal asymptote. So your graph will have a horizontal asymptote at y equals 0 if the original graph, f of x, either gets really, really big y values, either positive big y values or positive negative y values. And again, we'll see why that happens. As a point, if you had a point with a really, really big y value, when you change that y value to 1 over y, it becomes really, really small. And it keeps getting smaller and smaller and closer to 0. And that's why there's a horizontal asymptote there. I'm going to add to step 4, and I get you to write this in. Just plot some nice points. We've done this with every single graph. If you have a nice point, plot it. One of the really, really nice points are the invariant points. If you have a point where the y value is 1 or the y value is -1, what happens when I change 3, 1 to 1 over 1? It doesn't change. What happens when I change 5, -1 to 5, 1 over -1? It also doesn't change. Those are nice points. But any coordinate that you have, if you had, like when I'm talking about nice points, right? If I have the point 6, 4, that's a nice looking point. What's going to happen to it? All that changes is your y value becomes 1 over y. So any kind of nice points you have, you can change that. It's another nice point. This 4 and 5, when I refer to it, when we're doing our steps to try and streamline things to make it even easier, it's also a nice point. If you have a maximum or a minimum, it's probably going to be a nice point. So if you have 3, 6, that's a nice point. It'll change to 3, 1 over 6. But one of the things that we'll notice is that if you had a maximum in a certain area of your graph, it will become a minimum in another area of your graph, in the reciprocal graph. So we'll see what that looks like when we do some examples. And finally, once you've got a bunch of points, you've already done this in your rational functions unit. You can draw your graph towards your asymptotes. You've got a bunch of points, and you can just finish by showing the asymptotic behavior. So on the second handout, what you have is a bunch of examples and a step-by-step connecting it to the notes that are there of what you would do in each step. But what we're going to do looking at these examples is show the kind of work that you would do if you were solving this equation. So if I wanted to graph y equals 1 over x squared minus 4, I'll do step 1, and I'll draw x squared minus 4 first. So that's a parabola shifted down 4. It has an x-intercept at 2, 0, a vertex at 0, -4, and another x-intercept at -2, 0. Okay? And if I would like to summarize my steps really concisely, okay, what we're going to do to graph this is we're going to do all of our asymptotes first, followed by our nice points, and then I'll write asymptotic behavior. But that's where we just graph it in the end. What makes a nice little acronym? ANA. If you're like, oh, I don't know how to graph, what would ANA do? And then you can say, oh, she would probably do asymptotes, nice points, and then asymptotic behavior. Perfect. So we've got our original graph. When graphing the reciprocal function, where will we have asymptotes? We will have asymptotes at non-permissible values. And if you remember that the only thing is that your y values are changing to 1 over y, wherever you have x-intercepts to begin with, those will always become vertical asymptotes. So we'll have those two vertical asymptotes, and we'll label them x equals -2 and x equals 2. And since the y values in our original graph, see there's arrowheads going up forever, that means your y values are getting bigger and bigger and bigger. And every time that your y values either go towards positive infinity or negative infinity, you will have an asymptote at y equals 0. Step 2. Let's do some nice points. Well, so far the only nice point I've labeled is 0, -4. But I can show where that point will be. It'll be at 0, 1 over -4. Think back to your parabola here. Y equals x squared minus 4. Can you tell me another nice point? What happens when x is 1? What's y equal to? If I graph this point here. 1 comma, and all you have to do is a table of values. All you have to do is plug the value of 1 in. If I plug in 1 for x, I'm going to get -3. And so where does that point go? Well, the only thing that changes is your y value becomes 1 over -3 then. What's another point? What happens when I plug in 3? Can you see that I get 3 comma 5? Where is that point going to go? Three comma 1 over 5. -1, 1 over -3. And because it's a parabola and things are symmetrical, you'll also have -3 comma 5. So I would have -3, 1 over 5. I did a bunch of nice points. You could do even more if you wanted to. But once you have nice points in each section, you can go to step 3 and you can draw your asymptotic behavior. It's got to go through that point towards the asymptote, through these points towards the asymptote. Maybe you want to write a note that a 1 over f of x graph has no x-intercepts ever. Remember, the only time a function has an x-intercept is when y is equal to 0. And the only time a fraction is equal